Hello everyone, I would like to present my study on the topic stress intensity factor solution for those clad defect and underclad defect in WWER reactor pressure vessel nozzle under pressurized thermal shock. Written fracture assessment is central requirement in the safety justification of nuclear first-class equipment and the reactor pressure vessel. The allowable operating time of an RPV is ultimately governed by its resistance to brittle fracture, whose measure decreases with neutron irradiation over the planned lifetime. The overall assessment procedure is separated into complementary tasks: characterization of the material fracture toughness and its evolution under a gain, and evaluation of stress intensity factor driving any postulated defect. The present work addresses the second task, and more specifically the development of analytical or semi-analytical sieve solution suited for rapid engineering evaluation in WWER 1000 nozzle area containing austenitic cladding.
Nowadays, the issue of calculating sieve insert PV nozzle area remains unresolved due to the lack of a unified solution that take into account the specific characteristic of actual structures. The main specific problem and the background to the research are as follows. The presence of austenitic layer on the inner surface creates a two-material interface, which significantly distorts the stress field. The cladding effect increases significantly as the correct side decreases. This requires more specific modeling than that is currently offered by standard code. Current code designed for homogeneous material and do not take into account the effect of cladding. Polynomial methods work well for simple cylinder. We won't adopt this method for complex shape of nozzle.
The structure of the study is presented on the slide. It highlights a case stage of the work from initial modeling to the final analytical result. A series of high-precision finite-element models of nozzle zone were developed. We investigate how the cladding affects stress distribution at the interface and quantify the error of polynomial approximation in this zone. A database of influence coefficient was created following the overlife procedure. This influence coefficient was created for two limited cases of the elastic model ratio. We refined the influence coefficient using the least square method. This was done by using data from full emergency scenarios. We developed a unified approach for the from 5 to 15% correct size range by introducing a modified ellipticity coefficient.
The results for 4 emergency scenarios are presented on this slide. On the left part of the slide, we can see the result of the refined coefficient. You can see that the FIA data and analytical calculation match almost perfectly at every point in time. This is true for all considered correct diff. On the right part of the slide, the unified solution is presented. While there is a small deviation for different correct depths, the error for both aspect ratio 0.3 and 0.7 remains stable throughout the process. In conclusion, the proposed coefficient and the general solution offer a practical, computationally efficient tool for engineering fracture assessment of cladded WWER nozzle area.